Okay, so in this sort of week's set of lectures, we'll be looking at fractals. And you may be thinking, well, fractals, they're very nice, they're pretty pictures. What have they got to do with graphics and virtual environments? Well, in the second lecture today, we'll be looking at random terrain generation, which uses the concept of fractals. But for this morning, what I'm going to do is I'm going to do a quick lecture of what fractals are and some of their properties, and introduce some common, well-known fractals. Okay, so what is a fractal? Well, the word fractal was coined by Mandelbrot in the late 70s, and it's a word he gave to a shape, a geometric shape, which can be generated using a set of recursive rules. So remember recursion, we looked at it briefly when we looked at filling algorithms. Recursive rules are things which are applied within each other. Okay, so it's a set of mathematical rules. You apply the rules and you can draw pretty pictures and pretty shapes. Now, fractals exhibit what we call a self-similarity property. So in mathematics, similar means the shape is the same but at different scales. Okay, so the self-similarity property means that the fractal looks the same if you zoom into it. So if you have a fractal is just a shape or a pattern, if you zoom into it, you pick a portion of that shape and zoom in, that zoomed in area resembles the whole shape as it is. So that's what we mean by self-similarity. And this property is replicated in nature. So if you look at a cloud, a little cloud tends to look like a big cloud. Landscape, which we'll be looking at later on, and this is also your final assignment, be able to generate a random landscape. The landscapes also have this self-similarity property. Plants, the classic example with plants is the idea of broccoli. So you get broccoli, and you get a floret of broccoli. It looks like the whole broccoli plant itself. What we're going to be looking at today, ignore the today and Friday, looking at methods to generate these fractals and then apply them to landscape generation. So this is what I mean about nature. Okay, so for example, here we have some ice crystals, and they form a fractal in nature. For example, a snowflake. Electricity, so lightning strike. So electricity tends to go in these sort of forked arcs. If you just pick a little fork, if we zoom in, it tends to resemble a thing on its own. Got some Romanesco broccoli there. Anybody ever had that? Don't know, I've never had it, but yeah, some broccoli. And another classic example is the fern. So if I was to let's take this sort of offshoot here, this one resembles the whole fern. So that's what we mean by self-similarity. Okay, so what I'm going to go ahead and do is just talk about some very, very common fractals. And the first one is called the Cantor set. It's quite a boring fractal, it's not my favourite, because everyone has a favourite fractal. No? Okay. Right, so the Cantor set is sort of example of and the reason I'm using it is probably the simplest rule. And essentially what you do is you start with a line. So that's your iteration 0, or what we call stage 0. And the rule is we remove the middle third of our line. So at stage 0, this is our fractal, just a line. I've made it a bit fatter just so it's clearly visible. And so the first iteration, all I do is remove the middle third. So that gives me 2 lines. And now the second iteration, I take each one of these and I remove the middle portion, the middle third. So you apply it recursively. So for each new line, the next iteration, you just removed the middle third. And you keep going, and eventually, I mean, if I go any more stages than this, you probably get to a stage where we can't actually see each individual portion of the line. That's the Cantor set. Now, Cantor was interested in counting things.
Does n go on forever?
Can do.
Oh,
yes. Yeah, it's important. Yeah, we'll see in a minute.
I don't know how much you could zoom in. Is it gone forever?
Yeah, it can go through infinite. Yeah. It's interesting you said that because Cantor is involved. Have you ever heard of Aleph-0 and Aleph-1? Cantor's most famous with counting the number of numbers. And he showed that there's an infinity of all of the integers, and there's a number infinity for the real numbers. And he called the integer infinity Aleph-0, and he called the real number infinity Aleph-1. And it's a genius proof. So search Wikipedia for Cantor. Really nice proof of that. That's number theory, and that's Killian's domain. So, okay, back to fractals. Yeah, as n gets larger, n can go to infinity. We'll look at in a minute. Okay, so that's the Cantor set. Which brings me on. Nice segue, thanks, Joe. Brings me on to the fractal dimension. Now, the fractal dimension is essentially a measure of how complex your fractal is. So, we tend to deal with natural number dimensions. You've got this one-dimensional object, that's a point. Two-dimensional objects a line. Zero-dimensional objects a point. One-dimensional objects a line. A 2D object is a plane. 3D object is a volume, etc. Okay, so the fractal dimension, we can have our fractal dimensions being real numbers. So if you have a fractal dimension of, say, 1.5, then it's more than a line, but not quite a plane. You kind of get the drift. Okay, so fractal dimension is calculated using this formula. If n is a number of new elements added at iteration n, and epsilon is some scaling factor. Okay, and then we calculate it using this limit here. Log of this is a number of new elements added at iteration n divided by the scaling factor. So for the Cantor set, okay, how many new things did we add at the first iteration? There's 2, and the scale is 1/3. Each one is 1/3 of the previous iteration, and we've added 2 of them. Now for a 2D fractal, D will be in the range 1 to 2, so it's more than a line, not quite a plane. 3D fractal, the dimensions are range 2 to 3, so it's more than a plane, but not quite a solid. So let's have a look at the Cantor set. At iteration 0, we have one line segment, and I'm going to assume that the length of my segment is 1, just for ease. At iteration 1, we now have 2 line segments, and each one is 1/3 of the original one. At iteration 2, we've now got 4, and each one is 1/9. Iteration 3, we've got 8, 1/27, etc. So we can easily see that if we go to n iterations, the number of line segments follow 2 to the power n, and the length of each segment is 3 to the power minus n. Okay, so 1/3 to the power 3 is 1/27. Okay, so this gives us our n and our e. Oh, sorry, epsilon. So if we plug that in to our fractal dimension equation, okay, so the number of line segments at iteration n, well, we've seen that's just 2 to the power n. The scaling factor at iteration n is 1/3, or 3 to the power minus n. So I've taken the n outside. Okay, so using laws of logs, okay, take the power outside, put it in front of the log. Okay, well, n's cancel out, so therefore I've got no need for the limit anymore. Okay, and it gets down to log 2 over log 3, which is 0.6309. So what's this mean? Well, remember, a 0-dimension object is a point, a 1-dimensional object is a line. So this tells me the Cantor set is more than a point, not quite a line. Okay, so I introduced the Cantor set, fairly boring fractal, not my favourite. Just it's the simplest one to sort of be able to generate, to be able to analyse. This brings me on to the Cox snowflake. And this is an interesting fractal because it's a finite area bounded by a circumference of infinite length. So it's kind of a bit of a head scratcher, this one. And the rules for generating a Cox snowflake is you start with an equilateral triangle, and each side of your equilateral triangle, each edge, you remove the middle third and replace it by 2 lengths of a third to form a sort of 2 sides of an equilateral triangle. So divide each edge or each line into 3 lines of equal length, place an equilateral triangle so that the base fits in the middle third, and remove the middle line. So here's an example. So we start off with a line. Now this is just one edge of your triangle, so there will be 3 of these. You remove the middle line, middle third, and replace it with a equilateral triangle, and just take away the base of the equilateral triangle. So whereas at stage 0 we have 1 line, at stage 1 we have 4 lines. Each line is of length 1/3. If we do it again, each one of these edges gets the middle bit replaced by 2 edges of length 1/6 of the original. 1/9 of the original. And you keep going. Okay, so there's your starting, there's your iteration 0. Okay, iteration 1, 2, 3, don't know how long I've got. So in this one, each of these edges gets replaced. I'll keep going, and that's as far as those. If I go any more, you probably just wouldn't see the individual triangles. This is the Cox snowflake. Okay, so let's have a look at the fractal dimension. Okay, so at iteration 0, we have 3 sides. The length of each side is 1. Iteration 1, well, each of our 3 sides now has 4 lengths. So we've got 3 times 4. And the length of each of the new lengths is 1/3. Okay. At iteration 2, each of these lengths here is replaced by 4 lengths, and each of those new lengths is 1/27. So I can keep going, and you can start to see a pattern forming here. Okay, so iteration n, we've got 3 times 4 to the power n. As the number of, that will be my n on the top, on the numerator, and the scaling factor is 3 to the power minus n. So if I apply the fractal dimension formula, okay, simplify using laws of logs. Okay, hopefully this is not too. So what I've done here, use the multiplication law to split these up into addition, taking that n outside. Okay, therefore I can split this fraction up into 2. The first one doesn't, contains an n on the bottom, but log 3 cancel out, so that limit of n goes to infinity of 1/n. That's just going to go to 0. And I've just got log 3 over 4. Okay, which is 1.2619. So it's more than a line, not quite a plane. Okay, next one. This is fairly common. You see it in mosaics. Well, it's first attributed to, and I'm not Polish, so I can't pronounce that. Fractal, or I don't know the line for it is, but Serpents. And Serpents developed this triangle, but it has actually been seen in some medieval churches. So he wasn't the first to invent it, but he was the first to sort of formulate it. And essentially the rule is, or the rule are, start with a filled triangle. For each filled triangle, make an unfilled copy. So this is our stage 0. I scale this down by 1/2 and invert it. Okay, so if I scale that down by 1/2, flip it upside down and remove it from the center, I get this one. So therefore I've got 3 triangles, scale it down by 1/2, invert it, remove it from each center, I get that one. Okay, so that's the Serpents triangle. And I've used MATLAB here just to draw this one after, I don't know, about 6 iterations. Any more you can't really see. The resolution of the screen's not enough to really go too far down. So it's a nice pretty pattern. And you can see we have the self-similarity. So if I just take this triangle, the bottom left triangle, and blow it up, it's the same as the whole Serpents triangle. Okay, well that's one way of doing it. Okay, that's a geometric way, but we can also use what's called the chaos game. Okay, and this will give you the same fractal, but using a different method. Now, the chaos game, what you do is you start with a triangle, and you'll start at one of the vertices of the triangle, doesn't matter which, and you randomly select one of the 3 vertices of the triangle. Okay, so just use a random number generator or something like that. Find the halfway point from your location to that randomly selected vertex, and jump to that point and mark it with a dot. So now you're somewhere within the triangle. So then you randomly select one of the 3 corners, move halfway towards it, put a dot there. Okay. So we can write this as a matrix equation. So this is the translation. Okay, so x and y are your coordinates on your triangle. Okay, and this is your new pixel. And you randomly choose which way to go. Okay, so if the top vertex is chosen, okay, so this here is just from the definition of an equilateral triangle. Okay, so we go halfway towards the top vertex, a quarter and root 3/4 to our transformation. If the bottom right vertex is chosen, okay, so we have to add this, so just adding 1/2. And if the bottom left was chosen, we just do that. And this is what you do, this is what you get. I wrote a MATLAB program to do this, and this is after 1,000 dots. So there are 1,000 dots on there. Okay, obviously it doesn't look too much like the Serpents triangle. And if I go to 10,000, it's starting to sort of appear. And if I go to 100,000, you can see it's getting much better. So that's the Serpents triangle. Now, the reason I showed you that chaos game is just to show you there's more than one sort of method in which to generate these fractals. Okay, so we can use a chaos game which takes a random element, like rolling a die, which we'll be doing in the next lecture when we design our landscapes. But you can also do it in a geometric way. Okay, this is my favourite one. It is what's going to go on to talk about what's called the Mandelbrot Set. Now, this is named after Benoit Mandelbrot. He was the one who coined the term fractal. In his book, The Geometric Thing of Nature, I can't remember. It's referenced in the notes. Okay, Mandelbrot Set is the most famous one. Okay, in the 80s, there used to be a shop called Athena where they sold pretty much nothing but posters and sort of birthday cards. It's gone out of business. But one of their most popular posters was, as well as that, somebody holding a baby, the most popular poster was of the Mandelbrot Set. It was also pretty funky. Okay, what is it? It's a beautiful and complex shape. Okay, generated from a very simple iterative scheme. So we start with a very simple set of rules, and if you apply those rules, you get a very infinitely complex, or very infinitely, sorry, that's bad language, you get an infinitely complex pattern emerge. You may have seen it in Big Bang Theory. You're going to watch that QI opening credits. There's the opening credits of QI, and that's the Mandelbrot Set there. It also appears in quite a few different places. The Mandelbrot Set is defined on the complex plane. So we're going to have to just sort of refresh your memory about complex numbers. A complex number, Z, is made up of 2 parts. Z is my number, and I have a real part, which is A, and an imaginary part, which is B times I. A and B are both real numbers. I is the square root of -1. Or more accurately, it's more accurate to say I squared is equal minus 1. Okay, so A and B are real numbers, I squared equals minus 1. Obviously, in our sort of, if we were only dealing with real numbers, and I said, oh, what's the square root of minus 1? You say it doesn't exist. But with imaginary numbers, we're imagining it exists. And when we do so, there's lots and lots of useful things that come out from that. So A is known as the real part and is denoted as real Z, R-E-Z. B is known as the imaginary part. Even though it is a real number, it's known as the imaginary part and is denoted by ImZ. Now, we want to be able to perform operations on complex numbers exactly the same way as we've done using real numbers, natural numbers, integers, etc. Okay, so if we want to add two complex numbers, quite simply, we add the real parts and add the imaginary parts. Okay, so here I've got two complex numbers. I've stuck brackets around them, but that's not really necessary. I've just done that just to split them up. So the two real parts are 2 and 4, so if I add them up, I get 6. The two imaginary parts are 3 and minus 2, so if I add those two up, I get 1. So the addition of those two complex numbers gives me 6 plus I. Now the product is slightly more tricky. It's just done by expanding out brackets. So here I've got the same two imaginary numbers. If I calculate the product of them, okay, so obviously if I do FOIL method or smiley face method or whatever you want to do it, 2 times 4, 2 times minus 2i gives me minus 4i, 3i times 4 is 12i, and 3i times minus 2i is minus 6i squared. Now, remember, I squared is equal to minus 1. So I'm multiplying minus 6 by minus 1, so that gives me plus 6. Minus 4i plus 12i, well, that's just 8i. I can't get rid of that i. And I've got 8 plus 6 as the real parts, gives me 14 plus 8i. So I can add two complex numbers, and I can multiply two complex numbers. There are other operations on complex numbers, but I just, for this purpose, all I need is addition and multiplication. Okay, this brings me to the idea of the complex plane. Okay, so the complex plane is essentially, along the horizontal axis, I have the real part. So if I have a number z, and I want to plot it on the complex plane, z gives me the horizontal axis, and the imaginary part of z gives me the vertical axis. So that allows me to be able to plot a complex number on this plane. So for example, if I have z equals a plus bi, I go a across the horizontal axis, b up the vertical axis, and that's my point. Well, that's my complex number plotted on the complex plane. And the final thing, sort of the recap of the complex numbers I'll be looking at, is the idea of the modulus. Okay, and it's denoted very similar to magnitude in vectors, just to confuse things. Okay, single vertical bars either side of my complex number, and this is the distance between the origin of the complex plane and where my point is plotted. So very simply, what is this distance here? Okay, and using Pythagoras, you can see it's quite easy. This is just square root of the real part squared plus the imaginary part squared. That's a modulus. Okay, so the reason I just did a recap of complex numbers is because we use them in the generation of the Mandelbrot set. And essentially, this is what defines a Mandelbrot set. We have an iterative scheme. Z is just a complex number. And what this means is the n plus 1. So our point, similar to the chaos game, we're going to calculate the position of a point, mark it, move to a next point, mark that point, etc. So our next point is going to be equal to our current, the value of our current point squared plus some constant. Now this constant, this c, is the complex number. That's your start point. That's the point you start with. So a start point of C will give you a series of points Z, which we can calculate using this scheme here. And what we do is any point for which Z, or the modulus of Z, remains bounded, so it remains, the modulus remains within a certain value, that belongs to our Mandelbrot set. Any point where our Z, the modulus of Z, disappears off to infinity does not. Okay, so C is a complex number. Z0 is used as a starting value. So for your first iteration, you'll have 0 squared plus whatever complex number you have. And then you can, that will give you some value of Z, and then you continue from there. And what we say, this is an escape algorithm. We say the point C is escaped if its modulus disappears or gets greater than a certain value. Now, Mandelbrot used the value of 2, but we can change that to generate different fractals. Okay, so let's have a look at a couple of examples. Okay, so just to recall this iterative scheme, let's take the number 1. Okay, so 1 is my real part, 0 imaginary part, so I've just got the number 1. Okay, so that's what I start off with. Okay. Second one is I take Z0, square it, but plus my C. So this is Zn squared plus C. But at the moment, Z is 1. So I square it, but plus C. That gives me 2. And each time I'm going to calculate the modulus. So Z0, obviously it's going to be 1. Square root of 1 squared is 1. When Z1 is 2, square root of 4 is 2. So the modulus is 2. So now I've got a value of 2. Square it, add C, gives me 5. And therefore, the modulus of Z2 is 5. So this one's escaped. Okay, the modulus is already greater than 2. If I continue, you can see, okay, it's escaped here, but as you can see, it'll just keep getting bigger and bigger and bigger. So therefore, C equals 1 plus 0i is not in the Mandelbrot set. But what I'm going to do is I'm going to test this, but starting at I. So I've got 0 real part, 1 imaginary part. Okay, so for my starting point is just I, the modulus is 1. Okay, I squared plus I. Now I squared is obviously by definition minus 1 and plus I, so that's my Z1. And if I calculate the modulus, I've got root 2 because I've got minus 1 squared is 1, plus 1 squared is 2, square root of 2. Okay, so now I've got minus 1 plus I square that. Okay, so minus 1 plus I squared is 1 minus 2i minus 1. Okay, so the ones cancel out. Minus 2i plus I just gives me minus I. And this modulus is 1. Okay, square minus I. So I end up with plus I squared, which is minus 1 plus I, which is actually back to that one there. So that's root 2. It's going to be 1. It's going to keep cycle between minus I and minus 1 plus I. So it's going to go on forever. And it never escapes. It never gets larger, the modulus, than 2. So therefore, we then say that this number is in the Mandelbrot set. So on the previous slide, if I go back a few, C equals 1 was not in the Mandelbrot set. But C equals I is. Okay. And if I do that for lots and lots of different starting values of C, this is the image I come up with. So our first one, I chose 1, so that's that point there. Okay, so 1 along in the real part, 0 imaginary part, so I started off with that point, and it diverged. So that's not a part of the Mandelbrot set. The second point I chose was I, wasn't it, which is somewhere up here. So 0 real part, 1 imaginary part, somewhere up here. Okay, that was a member of the Mandelbrot set, so I coloured that point in black with a little black dot. And I've done that lots and lots of times. So every dot on this, this is, believe it or not, this is a raster plot. Okay, quite a high res raster plot. For each position on this plane, I've done that iterative scheme. And if it diverged, it's not a part of the Mandelbrot set. And it is white. If it didn't diverge, it remained bounded, I've coloured that pixel black. And that gives me the Mandelbrot set. Okay, so that's the shape. It's a very interesting shape. May not look at the moment, may look like a bit of a blob. Okay. This is going to just have a look at the convergence behaviour. So I'm going to select one point, which happens to be -0.5, and the real C is -0.5, imaginary C is 1/2. So I'm going to take that point there. And I'm going to apply the iterative scheme and just see where my point bounces around. So it sort of bounces around, and it keeps going, and eventually I get bored. So I'm saying, okay, that's not escaped. Okay, that's remained in bounded, so that is a member of the Mandelbrot set. Okay, I've taken a point now just slightly to the left of it. So that was my start point there. Now I've taken a point just slightly to the left, and I'm going to do the same. Okay, so if I start at that red point, okay, do a few iterations. So far so good, it's remained bounded, but it soon starts to diverge, and the distance from the origin becomes greater than 2. So that point there, my initial point, is coloured in white because it's not a member of the Mandelbrot set. Okay, that's fairly black and white, fairly boring. Let's add a bit of colour. This is what I call hippie maths. It gets all psychedelic from now on. Okay. Our Mandelbrot sets do not plot the points that aren't in the set. So at the moment, they're just white. But what we can do, we can make it really trippy, and we can colour these points depending on how quickly they diverge. So how many iterations did it take for their modulus to be greater than 2? So what we do is we have a matrix M, and that matrix keeps track of the number of iterations it took to diverge. And we can also normalize this iteration count so the colors look smooth. Okay, and we normalize it with using this sort of log scale here. Okay, so this plot, quite simple to do in MATLAB, by the way. All these, they're not too tricky. What I've done here is I've colored them in. For those points on the plane which diverge quickly are coloured in blue, and those points on the plane which diverge slowly, they're sort of dark red, and there's some sort of colour map in between. Okay, so this gives you a clue on how far away those points are from our Mandelbrot set. Not in terms of the modulus, but in terms of divergence. Okay, so that's normalised iteration count, and we can apply the, that's without normalized iteration count. Okay, so if we apply that log scheme, we can see we have a smoothing of the colors. So we get some quite sort of nice, trippy images. Okay, I mentioned at the beginning, we can zoom in on these fractals. Okay, so what I've done here is I'm going to zoom in on that top sort of portion there. Okay, and if you sort of squint and turn your head to one side a bit, you can see there's a mini Mandelbrot set there. Okay, so that's sort of the top of it. Okay, it starts to get a bit psychedelic from here on in. You listen to sort of Pink Floyd and imbibing some dodgy substances. You know, you can have a good time. But you can see the sort of jaggedy nature of it. Okay, we can keep zooming in. So here's a mini Mandelbrot set I found, and if I zoomed in on the same portion, I'd find it again. So I can keep going forever. Okay, this is sort of like the bit between the two, what we call bulbs, the main bulbs. So it's called the Valley of the Seahorses, because apparently these resemble seahorses, each one of these. Yeah, there they are. And yeah, some pretty pictures. Okay. This one, I zoomed in a ridiculous sort of number of times to find this itty bitty Mandelbrot set. And the point being is I could zoom in onto that and find that itty bitty Mandelbrot set in itself. So I can keep going forever. What am I going to try and do actually? Scripts on YouTube, everyone likes YouTube. Whether to turn the yeah, there's a bit of a dodgy song on this one, but well, it's got a good animation. Yeah, I'm turning that song off. But this is animation where somebody's done. They zoom in on the Mandelbrot set. Keep going, and you sort of gets a bit trippy, like I say. Keep going. You'll find other little Mandelbrot sets in there. Some eventually. Oh, you wouldn't want to be on medication when looking at this. Oh, is that one? There we are. You can zoom in on the same point as that one. I think I'm going to stop there. Okay, so if we zoomed in on the similar point, yeah, on the same bit, we'd find it again and again and again. Okay, so that's Mandelbrot set. I mentioned also at the beginning we can look at the idea of in nature, and I haven't seen anything in nature that looks like that. But we could use fractals to actually generate plants. Okay, so classic example is the shape of a fern, and Michael Barnsley suggested this chaos game, and what this is, starting at points x, y, any point, writing that random number between 0 and 1, and depending on the value of the random number, would depend on where you go next. Okay, so if your random number is less than 0.01, we apply this transformation. So essentially, just add 0.16. Well, multiply y by 0.16. If it's between 0.01 and 0.86, we apply this one. 0.86 to 0.93, etc. Okay, so these are different probabilities. So with the random number, you've got a probability of moving a particular direction. Okay, so that's a chaos game. Okay, so we're going to generate the Barnsley fern. That's done using about 1,000 points. Okay, you can't really see much there. But as I increase the number of points, okay, eventually we get the fern. Okay, so that's just done by using those 4 different, depending on where we are, it's effectively choose a random number, so 0, 1, and then that decides where you go next. Okay. And that brings me on to fractal landscapes, which I'm going to cover actually. No, I might as well start. I've got a few minutes left. Okay, so the point of me looking at fractals is not that I'm going to ask you to generate the Mandelbrot set, although it is good fun. If you want to do it, it's a good programming exercise. It's not too difficult either. But it's about random landscape generation. Now, often modern games have huge sort of virtual worlds, and rather than defining each individual vertex in that virtual world, the game developers write a landscape generator, and they use fractals to do it. Okay, the reason you can do that with landscape is landscape generally follows a self-similarity property. So if you take the landscape, a mountain as an example, if you zoom in on, if you have a mountain and you zoom in on a peak, that looks like, resembles the mountain itself. If you keep zooming in, you get a little rock, that looks like a mountain. So different scales have the self-similarity property. Okay, so we use fractals to do that. the example of the fractal method, well, one example is what's called the midpoint displacement algorithm. Now, this is not to be confused with the midpoint algorithm for drawing circles. Okay, midpoint displacement. Essentially, what you do is you start off with a line, like the Cantor set. You take the midpoint of the line and calculate its location. Okay, so for example, the midpoint I've denoted as yi plus a half multiplied by the two endpoints. So in other words, you find the average, calculate the midpoint. And then what you do is you push the midpoint up or down a bit, okay, by a random amount. So you calculate the midpoint, and then you add r to the y coordinate. And r is some random number. But r is in the range r min to r max. Okay. For the next iteration, what you do is you reduce this range and then keep going. So for example, let's say we halve the range. So for the early iterations, your r is going to be a random number between have a larger range. For later iterations, the range reduces. Okay, and then all you do is repeat steps 1 to 3. So here's our example. Start off with a line, and I'm going to move that midpoint up. Okay, so the midpoint was here, and I randomly moved up or down. Now I have 2 lines. So for each of these 2 lines, I'm going to calculate the midpoint, and I'm going to move them in a random direction, either up or down, by a random amount. Okay, so that dot dash line there was what the older one looked like, and then so the midpoint, and then this one I moved up, and that one got moved down, totally randomly, by the way. Okay, so now I've got 4 lines. Do the same again. Take the midpoint, move them up or down. If you keep going, you get something which sort of resembles a landscape. Okay, you got to sort of. I know it's only in 2D. You got to sort of, I don't know, suspend your disbelief a little bit. Okay. So that's the midpoint displacement algorithm. Okay, well, we can control how rough our landscape looks, right? If we have a look at this roughness parameter. Okay. So the amount by which the midpoint is displaced is a random number sampled on this distribution, which is reduced. So for example, if you halve it, which is kind of the most common method, if we start with the range -1 to 1 on your first iteration, your second one, you halve it, so -1/2 to 1/2, -1/4 to 1/4, etc. Well, we can actually have a control on how rough the landscape looks, whereas if we use this for our range. Okay, so we have 2 to the power -2n times h. N is your iteration number. H is what we call a roughness parameter. That's in the range 0 to 1. So if h was a half, -2nh would just be -n. Okay, and we'd have this one here. So when h is a half, we're just halving the range. When h is 0, the range is 1, because it will be 2 to the power 0, and the range of which values you take your random number from are always the same. So eventually you just get a random sort of noise, really, random jagged. Okay. And then when h is 1, we got 2 to the -2n. So the range is quartered at each stage, and you'll get a very, very smooth landscape. Okay, so those are the 3. Well, those are 3 examples. What I've done here is I've generated my midpoint algorithm using a half, and then I've reduced it to 0.2. You can see it's much more jaggedy. And if I increase it to 0.8, it's much more smoother. So that roughness parameter h determines how rough your landscape is. And I'll just show you. I'll bring up the code in the next lecture because this is important for your final assignment. But I'll just show you the output. Okay, so I wrote a MATLAB program to do this. Okay, so starting at stage 0 with a line, and this is totally random. So if I show you some iterations, eventually you get to that. Sorry?
This is how you do mountains and all that.
Yeah. So that's how, for example, that would resemble a mountain. Obviously, at the moment, it's just in 2D, and we're dealing with a 3D virtual world, so we need to extend that to 3D. And that's what we'll be looking at in the next lecture. Okay. Any questions? Okay. So, yeah, so see you in a couple of hours' time when we'll be looking at the 2D algorithm.